All right, we're recording. So before our break, I know it was a while ago, I gave you permission not to be here. The video is online, so I hope you watched it. You had like 11 days. If you haven't, make that part of your homework to get caught up on section 6.1. It's super important. This whole unit ties together with what we talked about previously. So just to refresh your memory, we talked about a specific type of function in section 6.1 called a one-to-one function. And the definition of a one-to-one function is, well, first off, the definition of a function is it's a relation in which each x value corresponds to a single y value. A one-to-one function makes that a little more specific and says not only does it correspond to one y value, corresponds to a unique y value. That's why it's called one-to-one. And the reason we talked about one-to-one functions is one-to-one functions have inverses that are functions. And so things we talked about, in case you haven't watched the video, are how to identify one-to-one functions, how to find inverses, how to determine if two functions are inverses. So you're responsible for all of that, whether you were here on the Thursday before spring break or not. And so what we're going to talk about now in section 6.2 is a specific type of one-to-one function. So we are getting a new basic function. So we have our 6 basic functions from way back in chapter 2, x cubed, x squared, square root, cube root, absolute value, and then the identity y equals x. Then we got 2 new basic functions when we talked about rational functions, 1 over x and 1 over x squared. And here is our new basic function, okay? It's called the exponential function. And again, we're talking about this because it is a specific type of one-to-one function. So an exponential function is something we have not seen before. It has the exponent, it has the variable in the exponent, so that makes it fun to deal with. So just for terminology's sake, where the 2 is, that's called the base. In case you don't remember, the x is called the exponent, and that's why this is an exponential function. So to graph this, what I'm going to just do is I'm going to make a nice table of values. It's what I recommend you do, because for each of these, the shape of the exponential function changes depending on its base. Okay, so for instance, I'm just going to pick these values just to get used to doing it. I'm going to pick 4 and 3 and 2 and 1 and 0, -1, -2, just to have a nice variety of things that I'm plugging in. And you've got your calculator. You can multiply in your head whatever you want to do. But when I put a 4 in, what is 2 to the 4th power? When I put a 4 up there in the exponent, 2 to the 4th is what? Little more, 16. Okay, 2 times 2 is 4, times another 2 is 8, times another 2 is 16. Now that's going to be a little too big for our graph, but I wanted to use that as a warm-up. So the next one is 2 to the 3rd. What is 2 to the 3rd going to be? 8. That time we've got 8, yes. 2 to the 2nd. 2 to the 2nd is going to be, 2 to the 1st is going to be 2. Here's the big one. 2 to the 0. What is 2 to the 0? It is 1. Yes, thank you. 2 to the -1. Negative exponents mean the base is in the wrong place. So that is going to be 1 over 2. And then last but not least, 2 to the -2 is going to be 1 over 2 squared, which is 1 over 4. Okay, in case you've forgotten how negative exponents work, 2 to the -1. 2 to the -1 means you flip that base and it becomes 1 over 2. 2 to the -2 becomes 1 over 2 squared, which is where we got the 1 over 4 from. That's how that works. Now I'm going to plot those points, and this is our basic exponential function. So here we go. I'm not going to plot 4 and 16. It goes off the grid, but I am going to plot 3 and 8. So put a nice dot right there at 3 and 8. The next one's at 2 and 4. So woohoo, there we go. My next one. The next one is at 1 and 2. Then 0 and 1, then -1.5, and then -2 1/4, and we'll slip a dot in right there. And so what we get, some people call this a J curve. Okay, it's an exponential curve. It never goes through the x-axis. Okay, so the x-axis is a horizontal asymptote. You're never going to put a value of x into the exponential. That's going to give you 0. That's one of the big things. So in case you're wondering, hey, what does the Perkster look for when he grades my test? I look for two things. I look to make sure that you don't put that through the x-axis. And then I also look for to make sure that you're not curling it back up. So I'm going to extend this just a little bit more. So the exponential curve, as it gets close to the axis, it's like a plane that's coming in for a landing that's never going to quite hit the runway. That's an exponential curve. In a biology class or an economics class, you might see that as an example of exponential growth. Okay, so that's an instance where it might be used. So let's answer some of the questions about this this exponential curve. What is the domain of this? What are my x values? How far left does this go? Negative infinity, fantastic. How far right does this go? That's true. So there's my domain, negative infinity to infinity. My range, what's the lowest the y values go? 0, but since it never equals 0, because I told you it never goes through the x-axis, I'm going to put a parenthesis there. And then how high does this get? Infinity. Here's a question that's a blast from the past for us. That function, as I go from left to right, as I trace it from left to right, is it an example of an increasing function or is it a decreasing function? It's increasing, so I'm going to circle that. Yep, it's increasing. And then just to reiterate what I said before, the reason we're talking about this now is because this is an example of a one-to-one function. Just to review, I know it's been a while on spring break, so I'm just trying to get your brains jump-started and moving. What is the visual test I can perform to see if a function is one-to-one? Horizontal line test. Yes, and this clearly passes the horizontal line test. I can draw little horizontal lines, and it never goes through the graph in more than one place. Excellent. So what we're going to do for the next couple minutes is just going to practice graphing this basic function. So what I'm going to have you do is I'm going to change the base slightly in exercise 1, and I'm going to give you 2 minutes, and I would like you to make your table and go ahead and graph 3 to the x power. It's going to look fairly similar, but the shape is a little bit different of 3 to the x than 2 to the x. And then answer the questions down below, and we'll check in with each other in just a minute. If you need me for anything, wave your hand, let me know. I'll come to you. Happy to help any way that I can. I want you to do amazing on this next test that we're going to have. So I'm going to go ahead and just get started. Keep working if you're working. If you have any questions, feel free. We're going to do another one in just a minute. So 3 to the x power. So I'm going to put my numbers in for the variable x. So the first one is 3 to the third. I just picked this as a warm up. 3 to the third, 3 times 3 times 3 is 27. Well, that's clearly not going to fit on my grid, but it was fun to do. So then 2, 3 to the second power, 3 times 3 is 9. Is everyone tracking where these values are coming from? You know where I'm getting these y values from? Okay, 3 to the first power is 3. 3 to the 0 power is 1. 3 to the negative 1 power, again, when I put in a negative exponent, that's telling me to change my base, so that becomes 1/3. And then 3 to the negative 2, I'm going to make that 1 over 3 to the second, and that becomes 1 over 9. So there are my values. Most of those are worth using. A couple of those are not really great for my grid. So 2 and 9, there's my first value. 1 and 3, second value. 0 and 1, negative 1 and a third. I'm not going to bother with the 1/9 because I'm not that good of a drawer. So this is what this is going to look like. It's another J curve. And there you go. Notice this one is increasing again. I'm pretty sure that you would have circled that, but it's increasing faster. That's the difference in the shape. I made my base a little bigger and it made this increase a little faster. The domain is the same as before, negative infinity to infinity, and the range is the same as before. So there's some things that are pretty consistent with my exponential function. Before I have you do another one, I don't want to rush through this because I know this is new and different and maybe the first time you've seen exponential functions. Is there a question about what I've done so far? Okay, well, I'm trusting you to be honest with me because there's no reason not to be. I love answering questions. So let's do another one. What I would suggest is for this one, since we've got a fraction in there, if you want to get good values, I would just suggest negating all the values of example 1. So what I mean by that is probably doing something like this and saying, okay, I'm going to do -3 and -2 and -1 and 0 and 1 and 2. And give those will be my suggested x values to make this as easy a process as possible. If you need me, wave your hand. I'm here. I can see the wave, even though I'm not wearing my glasses, I can see you waving your hands. I'm going to start putting these values in. Again, if you have any questions, don't hold back. Okay, I want everybody to finish strong in this class and do well and have good memories of our time together. So -3. So when I put 1/2 in here and then I raise it to the -3rd, remember that negative exponent flips the base. So now, because of the negative, instead of a half, what's the base going to be? Heard somebody say it. Yeah, there's some authority. 2 to the 3rd. Yes. So we're going to flip it around. That's why I suggested putting some of those negatives in there, is to flip the base. So now 2 to the 3rd is 8. And when I put -2 in there, that flips the 1/2 to 2. So you have 2 to the 2nd. That becomes 4. Your calculator can also tell you all this too. So don't just take my word for it. -1, when I put 1/2 to the -1, that just flips the base to become 2. When I put the power 0, anything to the 0 power is going to be 1. When I put 1 in, 1/2 to the 1 is just going to be a half, and then 1/2 to the 2nd, a half times a half is 1/4. So I get just kind of the reverse values that I got for the first example, which is not unintentional. So I have -3 and 8, and then -2 and 4, and -1 and 2, and 0 and 1, and 1 1/2, and then a 4th. And so this one is the same sort of curve. If you compare it to the first one, it's just a little bit different. So there's my 1/2 to the x. What's the difference between this and example 1? What's the main characteristic? This one's decreasing, yeah. And so what's the domain? Again, the domain for my exponential is pretty consistent, -infinity to infinity. What's my range? Consistent for my exponentials, 0 to infinity. So what I wanted to illustrate with those 3 examples is just this basic fact of exponentials. So I'm going to write this in this blank space over here. So for the exponential function, which is f of x is equal to a to the x power, that's my exponential function. Now, for reasons that is going to be clear when we start to talk about the inverse of the exponential, when we come back next time, we are only going to consider bases that are greater than 0. Okay, we're not going to talk about negative bases, although those are wildly fun functions, but that's for another class in another place. And we're also not going to consider a equal to 1, just because it's no fun. It's the constant function. Okay. 1 to anything is just going to be 1. So we're putting those limitations on the base. That makes your life a little easier, the fact that we're not having negative bases, and the fact that the base is going to be 1. So for any exponential function that meets these criteria, here's what we got. If the value of a is bigger than 1, like our first 2 examples, like example 1 and exercise 1, then a to the x is an increasing function. I'm just going to write in parentheses that is example 1 and exercise 1. It's an example of growth. So you see that in a lot of different areas. The population of the Earth right now is on an exponential growth function. So that's exciting. And then if the value of a is between 0 and 1, okay, so like our exercise 2, so if you have something like 2/3 or 4/5 or 1/2 like we graphed, or 1/3, anything that's between 0 and 1, then a to the x power is a decreasing function. Okay. And that is exercise 2. Called decay. Great example of that is radioactivity. If you've taken any sort of science or physical science or chemistry, that occurs there. There's other examples I could name, but at some point, if you take enough science classes or business classes or something, you will encounter these functions for sure. Everybody got that written down? I don't want to go too fast, but I don't want to go too slow. I want to hit it just right if I can. All right, well then what you're going to do next for me is we're going to flip the page. Since we've got since we've got this one new basic function, I think you know what to expect on the next page. Exercise 3 says, okay, we're going to take that basic function from the first example, and I want you to do 2x minus 4. So I'm going to give you about 90 seconds. If you need to reproduce the basic function, go for it. The more practice, the better. And then what does that minus 4 do? Don't tell me yet. You'll tell me in a few minutes. All right, so here's my 2 to the x graph. I just reproduced it from the first page. You can make a table of values if you need to. Okay, so I've labeled it as 2 to the x. What does this minus 4 do to the 2x graph? Down 4. Yes, that's a minus 4 off to the side. It says take all of your function values and subtract 4. What I'm going to do first, just so that I am careful on my graph, I'm going to take that horizontal asymptote and I'm going to drop it down 4 so that I don't mistakenly go below that line. So there's my horizontal asymptote. And so now all my points go down 4. So down 4, 1, 2, 3, 4 to here. This one's going to go down 4 to here, down 4 to there, down 4. This one's going to go down 4. And then last but not least, down 4. And so here's my graph. Remember, translations do not change the shape of the graph. They just change its position. So that's the exact same J curve or growth curve that we had before. Any questions? We doing all right? Okay, well then move down the page. Exercise 4 is right below that. We're doing something this time with the 3 to the x graph. So again, go ahead and reproduce your basic 3 to the x graph, and then whatever that minus 2 tells you to do. All right, so in this case, this -2, so you can see I've reproduced the 3 to the x graph. Just remember those points, but if you had to do the table, that's fantastic. The -2 is up there with the x. What does that tell me to do to my basic graph? Yep, right 2. So all of these basic translations that we've had since the beginning of chapter 2, they're staying with us. So here is in pink my 3 to the x -2. The horizontal asymptote doesn't move because I haven't moved this up or down at all. So that is perfect and it's done. So one more, just reminding us of the things that we can do to graphs. Do this exact exercise 5, please. Doing something simple to the 1/2 to the x power graph. All right, so this time I got a negative out in front of my function. What does that negative tell me to do to all my values? You flip them. Great. You just make those y values the opposite. So instead of a +8, it's now going to be a -8. And the same thing's true for the +4 becomes a negative, and the 2 becomes a negative, and a -1, and a -1/2, and a -4. And so we get this reflected function right here. Beautiful. That's maybe the best exponential function I've ever drawn. So lovely. And you were here for it. All right, so those are our new graphs, reminding us of the translations. Does anyone have any questions or anything that I did not do a good job or I glossed over or you're unclear about? Okay, I'm going to ask you to do that on the test. Okay, that exact thing. I'm going to have you graph a basic function. I'm going to have you move it around. So be ready. These sheets are available online. Make up some new ones for yourself, and you can get the grids and just go ahead and practice. All right, so last thing we've got to do today is, since we've got this new function, we're going to solve some equations. So there are 2 types of exponential equations. Our book is very clever in labeling them. Today, we're going to talk about type 1 equations. When we come back with some new tools at the very end of this unit, we'll be able to solve type 2. And so then the natural question is, well, Perkster, what does it mean to have a type 1 equation? That is a fantastic question. What a type 1 equation is, what it means, what the book is telling us, it's an equation where we can make the bases the same. Okay, so it's an equation where we can make the bases the same. It's the easier of the 2 situations. We can do this now with the algebra tools that we possess at this moment. So that's why we're going to talk about them. So type 1 equations are equations that you can solve when you can make the bases the same. Now, if you still are unclear about what I mean about that, and I totally understand, then let's go ahead and talk about this first example. So I've got 25 to the x power. I've got 125. What base can I write both of those numbers as? Both 25 and 125 can be written as base what? 5. Perfect. Great. Well done. So 25 is 5 to the second power. So I'm going to write that as 5 to the second, and then I've got my x. And then on the other side, 125 can be written as 5 to the third power. Now, again, I know you're learning lots of algebra. I don't want to assume that you remember everything. I just want to do a the quickest possible review of the properties of exponents that I could possibly do. So if I had this, if I had x to the second times x to the fifth, what do you do in the case where you're multiplying the bases? What do you do with the exponents? You add them. Yes. So this is x to the 2 plus 5, or in other words, 7. If you have x to the second and you raise it directly to the fifth, what do you do when you have a base, or excuse me, an exponent raised directly to an exponent? You multiply them. So that would be 2 times 5, or 7. And then last but not least, if I have, excuse me, x to the fifth divided by x to the second, what do I do when I divide my bases? You subtract. So this is x to the 5 minus 3, or excuse me, 5 minus 2, or in other words, 3. Okay, so that's as quick review of that. If you need more review of properties of exponents, because we're going to encounter those a bit in this unit, then please let me know. But I'm going to use the middle one of those properties, the power rule. I've got 5 to the second raised to the x power, so I can multiply these two things together. And I have 5 to the 2x power is equal to 5 to the third. And now here's what we can do. I told you earlier, and we verified it visually, that the exponential function is a one-to-one function. So that means that these y values are the same if the inputs are the same. So I'm just going to write the rationale here. You don't have to write the rationale for me, but when you go home and you've had some time to forget about it, I want you to remember why we can do what we do. So because a to the x is 1-to-1, because a to the x is 1-to-1, that means if 5 to the 2x equals 5 to the third, then, and you don't have to write all this stuff right here, you can just go right to the next thing. Again, I'm just trying to give you the rationale. I want you to understand the why we can do this. So if 5 to the 2x equals 5 to the third, then that means 2x has to equal 3. The y values, the 5 to the 2x is a y value, the 5 to the third is a y value. Those y values can only be the same if the exponents are the same, the inputs. That's the property of 1-to-1. And we talked about that some. Again, if you haven't watched the video, watch it. It's fascinating. And now I can finish this. I can divide both sides here by 2. I'll write that down just because I feel like I got to write something down. And we get x is equal to 3/2. And since there's no limitations on the domain of our exponential, that is my answer, 3/2. So that's how you handle a type 1 exponential equation. When you can equate the bases, then you just go ahead and say, oh, okay, then my bases have to be equal. So give exercise 6 a try. Same thing, 4 to the x plus 1 power equals 8. Anybody got a question? Anything rolling around in your brains that you're not quite sure of? Just to give everybody a nudge, what is the base that we can make both sides into? What are we going to use? 2. Great. Keep going. We're going to use 2. All right, let's see how you did on this one. And any questions you have, remember, we're here to learn. So if you made a mistake, it's okay. If you don't see what the mistake is all about, that's an idea for a question for you. So you just told me a minute ago that the base we're going to use here is 2. So 4 is 2 to the 2nd power. And then on the other side, 8 is 2 to the 3rd power. Now I'm going to use my power rule. I have power to a power. I have 2 to the 2nd raised to the x plus 1. So I've got to multiply. So that's 2 to the 2x plus 2. I'm going to give you a little hint. Most common mistake students make when I put one of these on the test is forgetting to distribute right there. Okay, so don't forget to distribute. That 2 has to be multiplied by the whole x plus 1. And then on the other side, we have 2 to the 3rd. Again, this is the property because the 2 to the x is a 1-to-1 function. I can now say, okay, this has to be true only if 2x plus 2 is equal to 3. I'm just taking the exponents and putting those equal to each other. I'm not canceling the bases. It's nothing like that. It's just the principle of being 1-to-1. And so now I'm going to subtract 2 from both sides of this. So when I do that, I get 2x is equal to 1. I'm going to divide both sides by 2, and I get x is equal to 1/2. And there's my solution to that exponential equation is 1/2. Anybody do something wrong and you don't see what you did or why it's wrong? Well, if you did and you're just being shy, when you start the next problem, raise your hand. I'll come over, help you out any way that I can. Because again, I want you to do amazing on this next test. But in the meantime, do exercise 7. Very similar problem to what we just did. Once again, just to give everybody a nudge, what base are you using on the left and the right? 3. Perfect. Keep going. All right, so on the left side of this, 27 is 3 to the third. So I've got my 3 to the third representing 27, and then the 4 to the x powers around that. And on the right, 9 is represented by 3 squared. So I've got my 3 squared, and then my x plus 2 is around that. Now I'll use my properties of exponents. So I have 3 to the 3 times 4 is 12x on the left. And then I have 3 to the 2x plus 4 on the right. Everybody with me? That's the difficult parts of the problem. Once you've done that, you should be good to go because now we can just make it into a linear equation. Okay. Because the exponential function is 1 to 1, we can now say, okay, if that's true, then 12x has to equal 2x plus 4. And I'm just going to solve that equation. I'm going to subtract the 2x from both sides. And when I do that, I have 10x is equal to 4. And then I'm going to divide both sides by 10, and I get x is 4 over 10, which is not reduced. So I'll reduce that by a factor of 2. 2 goes into 4 twice. 2 goes into 10 5 times. And there's my answer, 2 over 5. We just got one more problem for the day, so you're running out of time. If you've got a question, be sure to ask it. Do not leave here. Okay, I'm just doing one section today because I don't want to go further because I'm a realist. I know some of you haven't caught up, so make sure before you come back next time that you have done section 6.1, taken your quiz, so that you know all about one-to-one functions. And then you've done your exponentials and taken your quiz, because when we come back, we merge these two ideas of a one-to-one function and its inverse and the exponential. And we're going to talk about what the inverse of the exponential is. It's good times. In the meantime, exercise 8, last problem. What base are we using for this problem? Excellent, 2. Great job. Okay, so on the left side, I have a 1/2. A few minutes ago, when I asked what the bases were, I got the answer 2. How do I write 1/2 as 2? It's 2 to what power? -1, okay? The -1 tells me to flip that base, and that's where the 1/2 comes from. So I have 2 to the -1 to the 3 minus x power. On the other side, the 16, how many 2's make 16? 4. 2 times 2 times 2 times 2. So I have 2 to the 4th, and then x plus 2. Now I'm going to use the power rule on both sides of this. So on the left side, I've got 2 to the -3 plus x. Don't forget to distribute. On the right, I have 2 to the 4x plus 8. Again, don't forget to distribute. The fact that the exponential function is 1 to 1 says those y values, whatever they are equal if and only if, if and only if the exponents are equal. And now it's just a linear equation. I'm going to subtract the 4x from both sides to bring everything over on the left. So I subtract 4x, that gives me -3x on the left. I'm going to add the 3 to put all of my things without x's on the right. So when I add the 3, 8 plus 3 is 11. And then I'm going to divide both sides by that -3. A positive number divided by a negative number is -11/3. And so there is my solution to that exponential equation.